Thank you. Thank you to the organizers for organizing this workshop and inviting me also. Thank you. Um, so it seems to be tradition for me for events which are devoted to curvature to tell you how far you can get without curvature. So more or less, it was not intended like this, but that's more or less what will happen. So I'll talk about joint work with Fabrice Baudoin, my former PhD student then being Luo, and postdoc, my postdoc at the University of Connecticut, Rohan Sarkar. So, so how did we start with this? Was with Liang Bing when she was doing her PhD, and we wanted to prove log Sobolev inequality on an infinite dimensional Heisenberg group. So you might ask why you would be interested in this. Well, one of the things that I want to understand, some of my co-authors or collaborators, is how do you actually see that the corresponding operator is hyperelliptic? Because if you look at the definition of a hyperelliptic operator in finite dimensions, it really is very Euclidean, right? It's very difficult to see how you can even define it in infinite dimensions. And if you go back to what people did in infinite dimensions, which is probably Mattingly and Heirer, you can see different things that they did. But one of the ways to see this is to construct some toy models. So Heisenberg seems like if it's not hyperelliptic there, what else is, right? So that was one of the things that we wanted to look at. And of course, in infinite dimensions, any kind of regularity or functional inequalities are more difficult to get. So this is the motivation why we want to get some kind of functional inequalities which do not have dimension in constants. Okay. So I'll start with a relatively general result, which is about metric spaces. Nice metric spaces, because we'll see that at the end we'll apply it to weak groups equipped with sub-Riemannian structure. So in particular, the gradient, let's see if I can do it. No, I cannot do this. Okay, so the gradient will be horizontal gradient here, and so everything will be relatively explicit. So what we do, we just look at Markov probability kernels there, and of course the main example for us will be the heat semigroup, and so the kernel will be the heat kernel, hyperelliptic heat kernel, with respect to some reference measure. But one of the things that we did actually was not fixing any reference measures. So what are the functional inequalities that we're interested in? So here you have your gradient bounds, known also by different names, right? So that I did not mention here. Also, we are interested in a couple of reverse inequalities like Poincare and log Sobolev, mostly because this is what you usually get in the sub-Riemannian settings. So we have some building blocks for which we know this, and I'll also explain some of the consequences of having this. So it seems like a strange thing to prove, but actually they imply exactly the smoothness properties of the heat kernels, in particular in infinite dimensions, that I was interested in. And the last one is your classical log Sobolev inequality. And as we know, of course, you expect this constant C not to depend on the dimension, but also in the Riemannian case, it doesn't depend on the dimension when you take the heat kernel measure, but it does depend on the curvature, reach a curvature bound. So if you go to a sub-Riemannian setting, then the question is, can you prove it? What this constant is, what it depends on, and so on. Reasonable. So I'd say that what we use actually is very simple idea, which has two operations. One is tensorization, which probably will be not that exciting because it seems like, yeah, old stuff, especially for log Sobolev. But again, you can get very far with that, apparently. And there will be also another operation that I will not define here, but I will illustrate it with some examples. So more or less we'll combine some of these operations and control the constants in such a way that at the end we get some new functional inequalities on different sub-Riemannian manifolds where we know where the constants came from. You lose sharpness definitely when you do this, but at least we keep the dimension out of the constant, okay? So our basic theorem is that if you have a finite collection of these metric spaces with upper gradients and with some fixed Markov kernels, probability Markov kernels, we know that they satisfy one of these three inequalities. So here we only talk about gradient bounds, reverse Poincare, reverse log Sobolev. Then the product space satisfies the same inequalities with the constant, which is the maximum of that. Yes, I know that it seems like a very expected result, except that we dropped many conditions on the metric spaces, and the proof actually is quite different from what you would expect. And actually, I'm glad I can mention Kawada here because his result, Kawada's duality, is really fundamental in this approach. So what we didn't prove these inequalities directly, but we used some entropic inequalities using Wasserstein. Should I say Wasserstein, everybody else, right? Distance, yes, he's watching me. Actually, some other distances like Hellinger inequality going there. This tensorizes really well, and then going back through Kawada's duality to get this function inequalities. This is not a direct proof, but this allows you to control the constants. And of course, tensorization of log Sobolev goes back to, yeah, some other people, and it's a very useful tool, but we'll see how you, that we're not really interested in functional inequalities on this product, but other things that you can get out of that, okay? So it's a tool, but again, the proof really uses this other things that I'll mention at the end if we have time. Maybe it's a good time after listening to all the sub-Riemannian things to actually introduce the object that we're studying. So these are smooth manifolds, and by now we probably all know this, but still, so you have tension bundle, and only sub-bundle of this is equipped with the inner product G. And what we assume always is that it satisfies Hermander's condition, meaning that if you take linear Lie brackets or vector fields at each section, you get the whole tangent bundle section. So why is it nice? So you have natural distance there that I'll mention a little bit later. So this triple is called a sub-Riemannian manifold. You take the corresponding sub-Laplacian, and Hermander's condition gives you lots of different properties of the setting that are convenient. So on one hand, the corresponding sub-Laplacian is usually not elliptic, but hyperelliptic, so it has some regularity properties. We also have Chernyshevsky theorem, which tells you that not only you get a nice distance, so you get a nice metric space, but actually the original topology kind of stays the same. And another property that really takes care of lots of things that I kind of did not explain to you on the previous slides is that the sub-Laplacian actually has this nice property. So you have integration by parts, more or less. And this is your horizontal gradient, so you can view that as your definition. But there are different definitions here, okay? So it's the result of this is that sub-Riemannian manifolds have this natural structure that I described before of the symmetric spaces with upper gradient that has actually much nicer properties that, than general upper gradients. So we've seen this example, so I will skip it if it's okay, right? Heisenberg group, but we'll come back to more general settings there, which will be different from what we've seen, also Heisenberg groups. So the basic examples are Karnaugh groups, which have this horizontal and vertical splitting, which, so these are basic groups that you can think of, but at the end, we will not look at them closely. I will talk about some other examples. So what is this length structure that we have? So remember that in my first theorem that I mentioned, we actually assume that metric spaces are length spaces. In this case, it's really the this definition here is that you take a path and you only allow the tangent to be in this horizontal bundle, right? So you the movement is constrained into a much smaller sub-bundle, okay? And you only can measure things there. This is why you have to restrict it to this. And then you can define the length as here. And as I just said, this is a distance, which is usually called Kronecker-Isidore distance. And what we know is that it connects any 2 points. So it's a finite distance. So that's thanks to Chow-Rashevsky. Because we can connect any 2 points by horizontal path. That's the first thing. And then, and just to show us how things are, so for this talk, it doesn't matter. But in general, what we can think of as metric balls, they look very different from what we expect. And in this talk, it's not going to be so much relevant because we are not concerned about how it behaves, the sphere, and so on. But in general, it might be a problem. Okay, so here's a list of things that we should take into account before we go into functional inequalities. So the good news is that we have a nice gradient, horizontal gradient in this case. We have the corresponding length space, so we are in the setting that I went over very quickly. I know that. And the beginning, the first theorem. So there are some other things that might be a problem, which is, in general, you don't have a canonical choice of reference measure. So for Lie groups, we do, but for other more general sub-Riemannian manifolds, it's a little bit difficult to see what you should use there. The sub-Laplacian is not elliptic in general, it's hyperelliptic. And finally, we should mention curvature, right? So essentially, we mention it, that we cannot easily use it because we do have some examples and some settings where we have some techniques, as we heard even today, where you can have curvature dimension inequality of different kind, but in general, for general sub-Riemannian manifolds is not easily available, right? So the Markov semigroup that we want to look at is, oops, here I constantly think that it actually works. So the Markov semigroup here is really with respect to this hyperelliptic heat kernel measure, right? And this is what we are interested in. Okay, so let's remind ourselves what kind of bounds or estimates we want. So there are 4 of them, right? 4, yeah. And now instead of Markov kernel, I just take this heat semigroup. hyperelliptic heat semigroup. So the thing to remember now is that, which is an interesting thing, as we'll see, is that these constants now might depend on time, right? On how you run. Are we still okay? We all know this, right? Okay. Here are some of the known results here, and I'll explain some of the things that I decided not to include on the list of these inequalities, but to explain why originally we were interested in these results. So the first one is about Heisenberg group, and because it seems that this is what we all have to do, right, in this business, to understand Heisenberg group still. So going back to what was done before, so for the three-dimensional case, so it's for the Heisenberg group, three-dimensional Heisenberg group, we know gradient bounds. So this was done by H.Q. Lee. So for p greater than 1, it was done by Ty Melcher and Bruce Driver. That was her PhD thesis, but they couldn't get it for p equal to 1. Actually, the methods that they used was Malavans calculus. So it was an infinite dimensional proof of this finite dimensional result. H.Q. Lee gave an analytic proof, and what's interesting is also the connection to log Sobolev inequality, because in another paper he also showed that if you take this gradient bound with p equal to 1, you can actually prove log Sobolev inequality, and the constants are kind of very closely related to each other. More or less, it means that if you can prove this gradient bounds with some optimal constants, you will have the optimal constant for the log Sobolev inequality. We still don't know what that optimal constant is, okay? And we'll see some other interesting things that in this case, for example, you can prove that the constant that should depend on t, remember what I showed here, actually doesn't. You don't have. Okay, so what are other things that you can get from all these function inequalities? Again, for me, at least, it's not the subject in itself, right? But what else you can do with that? So for this reverse log Sobolev inequality, which looks strange if you've never seen it, you can actually prove something about the semigroup itself. And as I said, one of the things to, so when you think about hyperelliptic operator in finite dimensions, if you don't have this connection between Hermander's condition and regularity, you don't have regularity in infinite dimensions. Actually, what you can say instead is that the solution to the heat equation, for example, is smooth in some sense. And that you can actually interpret even in infinite dimensions. It requires some care, but you can do this. And this actually is how this whole bunch of two function inequalities are being used. So from this reverse log Sobolev, you can prove what's known as Fenny-Wang's Harnack inequality. And what it does, it actually compares your semigroup, right, at two different points. And it compares it with some coefficient here, which more or less all we need to remember is it depends on the distance between 2 points, because we want to see how smooth things are. So we want to take a derivative of something. And why this whole constant is in red here, because it's formulated here in terms of Riemannian manifolds with the Ricci curvature bound. And then you can see that it depends on this Ricci curvature bound. But actually, in reality, you don't have to have this constant there. Suppose you have some other object on which you can prove this kind of inequality with some constant that depends on the distance and some constant here. You can still derive the smoothness of the semigroup. More or less, what we see here is that So the main thing that we want is we want this quantity here not to depend on the dimension, because we take the dimension going to infinity, and whatever the constant there is, we'll take it, as long as it doesn't depend on the dimension. So this was exactly our motivation with Bruce when we did it in the Riemannian case for some direct or inductive and projective limits of finite dimensional Lie groups. And in particular, we use this approach for now sub-Riemannian case in infinite dimensions. So the first time we did it with Fabrice and Ty Melcher 10 years ago already. And it was exactly this tool. So more or less, at least my interest in this kind of inequalities was always how do you use them to prove regularity when you don't have PDE tools, okay? Is it okay? Okay, so now comes horrible part, because I tried to write it in the less dense way, but didn't manage, okay? So yeah, I still remember, Duncan told me, never put more than 5 lines on one slide. And yeah, I didn't manage. Okay, so more or less what I want to explain now is how we use this general result about product structure to prove something that we couldn't prove otherwise. Okay, so more or less it provides you with a way to prove functional inequalities on objects that you can build from some smaller parts for which we know these inequalities. So one of them is step 2 homogeneous kernel groups. So all these examples, at least this example is nice because you have a nice measure. So actually you know that the corresponding sub-Laplacian is nice. So all the technical things are not there. Where they are actually is that it's very difficult to control things when you try to do it directly. So actually you can write any step 2 homogeneous kernel group using a bunch of matrices here. So more or less, so we'll see that as an example. So of course, again, the basic example here is a Heisenberg group, right? Where you start with R to M and M is equal to 1. That's your basic example. And the modification you have is that in the center you have things that kind of split in different directions. So the main problem here is that you have some overlap sometimes, if it's clear. So if you go to the center of this group, you actually don't have several copies of Heisenberg, but you can end up in the same part of the center from different horizontal brackets. And to control this directly is, at least I don't know how to do this, but this is what we did. So this is not our result. It's been known that you can write any step 2 kernel group like this. You have very explicit way of writing vector fields very similar to what you have for the Heisenberg. And all you do is you have this even dimensional horizontal space. You put your inner product there. We assume that this particular vector fields are orthonormal basis. You take the sub-Laplacian. And as I said, this is 3-dimensional Heisenberg group. But if M is even and if n is greater than 1 and m is 1, you just get 2n plus 1 dimensional Heisenberg group, okay, with certain choices of these matrices. Okay with this? So it's just a bunch of matrices. And again, how do you deal with this? So the problem, as I said, is that if you take the group itself, then there is this interaction in the center that doesn't allow you to prove this inequalities directly. But what we did with Langbing last year was that you can actually take Heisenberg groups, take a product of them, 3-dimensional, and come up with some submersion, which I haven't defined, but I can explain what it is, to this group here. So this is exactly the second part, the second map that you can use to produce this function inequality. So as I said, the tensorization was done separately. And then after this, you usually employ some other map, which requires more of a skill than anything else, because there is no theory how to come up with this. And if you can find it, and if you can connect the sub-Riemannian structure on this tensor product with whatever you have here, you should be able to transfer function inequalities on each piece here to this thing here. And actually what happened was we started with a completely different project with Fabrice and Rohan, but this is where we ended up doing. I don't remember why, actually. Probably mentioned something, and then oops, what's that? Software. Main thing is not to push OK button. Yeah, I got that. Okay, so just to remind us, so we know some results for each piece. So we have not just Driver-Melcher inequality for p greater than 1, we have HU Lee inequality for p equal to 1 when n and m are 1, so for each of these pieces. So we have reverse Poincare, reverse log Sobolev, that's from this paper in 2008. And so what you get for free here is that you get these inequalities with the same constants on this group here. I have no idea how to prove it directly. So there are some, I should mention here that also in the paper, in the results that I will mention later, that some of these inequalities were proven in previous papers. And the main difference is that in almost all of them, if you can trace the constant, it depends on the dimension. So one of the results of what we did was really the constants that you get here, really, they use the same constant as for the three-dimensional case. So the dimension doesn't appear ever. Okay, so then we started looking around to see if we have any other objects that we can tensorize. And yes, you can take three-dimensional model spaces for the sub-Riemannian geometry, which connected Lie groups with Lie algebra, which has very similar bracket conditions, except this constant row is different, and you get three different. So Heisenberg is flat, SU2 is round, SL2 is negative curvature, the usual thing. Okay, and actually you can prove curvature dimension inequality, generalized curvature dimension inequality for this, and of course some of this goes back to the paper of Baudoin and Garofalo, but also what we used actually mostly is this paper in 2009, and what you get as result is reverse Poincare and reverse log Sobolev. So more or less, again, we were not interested in expanding this curvature dimension inequality because we did try before and it didn't work so well. But at least for these pieces, you have it, and you actually have the this function inequalities we were interested in. Okay, so what we do then, we take tensor products of different collections of these groups. This is the group I'm describing here, so it's another slide that I'm not proud of. So again, you take pieces not of just Heisenberg group, but SU2, SL2, if you want. You have some interaction in the next layer. So now we don't have Karnaugh groups anymore, right? So you have some interaction in, so you have horizontal space and the vertical space. So these pieces actually interact between each other. And so, of course, if you just take a tensor product as it is, then yes, you have these inequalities. What you don't have is if you have some interaction, then you might not have it. So we prove that under some condition, on this interaction, you actually prove all these functional inequalities. So then the question is, do you have any examples where you get anything new, right? And the answer is yes, I don't have too many examples, but one is S of 4. And for this, we really have no idea how to do it otherwise. So I don't have many more examples like this, but I'm pretty sure you can come up with some. So exactly, this is the kind of things that we were interested in, how you can actually, without going to the curvature dimension inequality, generalized or otherwise, how do you prove all these functional inequalities? And it seems to be, this might be a way to do this, especially because for this compact semi-simple groups, you always have a copy of SU2 or SU3 sitting inside of it. So this might be a way to kind of expand it to higher step type things, even if you're not dealing with Gardner groups. We still okay? I feel like I'm not doing well, but yeah, okay. Okay, so here's an example of another interesting result. So the question is, how do you control the constants in this case? So for the Heisenberg group, it was kind of clear that you get this wonderful maximum of all constants thing. That's what happens with tensorization. But here it's a little bit more difficult because you have this interaction that we want to take care of. And what we proved was the following interesting thing is that if you describe your interaction between these tensor pieces, right, product pieces, you get matrix, and actually looking at the spectrum of this matrix gives you the rate, gives you explicit constants. As I said, they're not the best ones. They're not sharp at all, but they don't depend on the dimension. You can take as large horizontal space as you want, right? But this will not depend on that, this constant. And actually, depending on how bad or how good this spectrum is, in particular, if it's this matrix is non-negative definite, then you get even more. So you see, this is really what you actually expect. Yes, for p greater than 1, but this is really the, you expect that if you have positive spectrum, right, you have some contraction when t goes to infinity. So we actually got more out of this. I decided to concentrate on these 4 functional inequalities. But in this case, you actually get more exactly because you know something about the building pieces, in particular, Li-Yao type estimates, real Harnack inequalities, things like that. So there are lots of consequences of this. And more or less, one of the examples that we should keep in mind is really is SO4, because as I said, I don't think any of the previous methods actually are applicable here. So I did mention that there was another map that we use besides tensorization, so I'll just probably illustrate it by something we did with Langbing Luo. So I will only mention this theorem, and then I'll give an example, the main example that we have. So what we looked at was a smooth manifold and Lie group acting on it. So it's G manifold. And actually, as we know, you can realize that as a Lie group mod some subgroup. This is what's useful at the end. And what we proved first that if you have this group G acting on M come with left invariant sub-Riemannian structure, then actually the manifold itself also has a natural sub-Riemannian structure. And if you can prove log Sobolev inequality for group G, then you can prove log Sobolev inequality for this homogeneous space with the same constant. Again, you lose sharpness, but at least you can do this. Okay, so it seems very abstract, not very clear if it's useful. And here's an example where I think some of the methods we've seen this morning are probably not always applicable, because what we wanted to do was to take Heisenberg group that is equipped with a different product. So it's non-isotropic. And therefore, some of the other things, including even generalized curvature dimension inequalities, are not really applicable here. Okay, so here's an explanation, and this has exactly relevance for this infinite dimensional case that I want to mention a little bit later. So we start with a 2n+1 dimensional Heisenberg group, which is equipped with non-isotropic symplectic form. I'll explain what it is a little bit later. Okay, and we have two other groups. One is product of three-dimensional Heisenberg groups, standard ones, and a certain subgroup of this, what is it? 3n plus three-dimensional object, okay? I'll also give you description of this. And what we did was we took, so we already know, thanks to HQ Lee, that we have log Sobolev inequality on each piece. So we have tensorization of log Sobolev, and then we can do this previous theorem, use it for this case, and then you get log Sobolev inequality for this large group with constant that comes from the three-dimensional one. So you distort it, you take products, and you still get the same constant, or you can at least prove it with the same constant. Okay, so yes, it looks horrible, I know. So more or less, we've seen this before, that Heisenberg group really is a Heisenberg group of a symplectic space. That's a different, slightly different take on this from what we've seen before. And more or less, it's you take central extension, as it's called, of this vector space by just real line. So you have the usual addition plus a correction term that comes from symplectic form. So what we've seen so far is standard symplectic form, but what we do instead, we actually take the sums of standard forms actually scaled by some parameters alphas. You might ask, why? Why would you do this? Because in infinite dimensions, you have to do it to construct the measure. So for convergence reasons, when you go to infinite dimensions, when you have n going to infinity, to construct the corresponding heat kernel measure, which we'll not talk about, but you can do it, you have to destroy the invariance you have. So the previous theorem then tells us that we can prove using HQ Lee result, which again, as I said before, you can connect the constants from the Driver-Melcher-Lee inequality and the log Sobolev inequality. They are connected like this. You can prove that actually this huge object satisfies log Sobolev inequality with the same constant. So this is what we proved several years ago, and I'll formulate it now in infinite dimensions. So actually, this point of view of Heisenberg group as Heisenberg group of some vector space is really the view that we took with actually Bruce Driver when we constructed it for the elliptic case. And you have all kinds of infinite dimensional problems here that you don't see so easily. And I think the dimension was part of the title of the workshop, right? So it's fitting that we have it here. So in infinite dimensions, quite often you have two different topologies, which means that you have two different objects here. One is this Banach space, centrally extended as we did before, and another is Hilbert space, which sits which is embedded densely into this one. So you think about this as your standard classical Wiener space of continuous functions on 0, 1, and functions that have, so Cameron-Martin in that case would be functions which are absolutely continuous with the derivative in L2. You can still define your symplectic-like form here and construct your Dirichlet form, which I tried to avoid for other constructions, but here it seems I cannot avoid this. So you can prove that it's closable, and well, this bilinear form is closable, so you get an honest Dirichlet form, and actually you get log Sobolev inequality with a constant that comes from finite dimensional, three-dimensional Heisenberg group. So the result here is that as in Rn, which I decided to skip, right, the classical gross log Sobolev inequality, if you take Gaussian measure, you get a constant that, depending on how you like your Laplacian, 1/2 or not, you get a constant that doesn't depend on the dimension. This is exactly what you have here, except that instead of Gaussian measure, you take the heat kernel measure that I didn't tell you how you construct, but you can do it, or we can do it. Okay. You still have a minute. Okay. So then you might wonder, okay, so you redid the example you already had before, so I'll now explain how you can get some other results. So in particular, yes, we have this. So one of the things that I wanted was to have a non-Lie group example. So Grushan plane is closely related to Heisenberg group, and so yes, you prove log Sobolev inequality in this way with the same constant as for the Heisenberg group. You can actually, so there are more examples there. So essentially, these homogeneous spaces allow you to go beyond what we looked at before. And so in particular, in this case, we also get log Sobolev on SO4 with sub-Riemannian structure, and that's what you get from this theorem. So I'll only mention very briefly the proof of the main theorem that we used in the first part. Maybe I'll just go to the next slide because we probably all know these definitions. I just wanted to mention again Kuvada's duality here because this was really essential. So we didn't want to prove these functional inequalities directly, as I said. What we did instead, we actually checked on the product manifold in this case, product sub-Riemannian manifold. We proved the right-hand side, right? And then you have this gradient estimate, for example, and you also get all kinds of other inequalities using this. And in particular, I wanted to mention that you also get this Wang-Tsarnack inequality with a very different constant here. Remember that in the Riemannian case, you have the Ricci curvature here, and we don't have it here. So these are really results for products of sub-Riemannian, for example, manifolds or metric spaces. And yes, I'm very careful not to say metric measure spaces because actually measure does not enter here directly, which was one of the reasons why we went this route, because otherwise you're always stuck on choosing something, and then, yeah, sometimes you have to pay for the consequences, right? So yeah, this is another wonderful slide, and I think it's a good place to tell you I will not prolong your suffering, and I'll stop here. Thank you.